sections we're supposed to be covering today? I would guess 2, but...
Yeah, 36 and 37.
36 and 37. All right. So 36, we're dealing with the greatest common divisor. The GCD is what we're going to use over and over again. And you know from grade school what we mean by greatest common divisor. When I say 6 and 24, what's their greatest common divisor? 6.
Yeah.
6 divides 6 and 6 divides 24. It's the greatest thing that divides both of them. So we define a divisor. We define a common divisor of 2 numbers as a number that divides both of them. And we define a greatest common divisor of 2 numbers as the greatest number that divides both of them. Now, I don't think I need to write out those 2 definitions here. I think you're comfortable with those, right? Don't need to write out. They put the exact definitions in the book, so those are well-defined terms. We mean a precise thing when we talk about a common divisor and a greatest common divisor, but they're exactly what you think they are. I don't think there's any tricks. Maybe the one weird thing that you need to remember is that negative numbers are divisors. So when I say what are the divisors of 6, that's negative 6, negative 3, negative 2, negative 1, 1, 2, 3, 6. Those are the divisors. What's the greatest of those? 6 is its greatest divisor. You might think for a second, why not negative 6 as well? Aren't 6 and negative 6 the same big? No, this is 12 more than this. Okay, that's all like the trick scenarios you might come across I can think of. So, divisor, greatest common divisor. Now we're going to get into what is called Euclid's algorithm. I believe it's the oldest known algorithm, and it's an algorithm for calculating the greatest common divisor between 2 numbers. So it's easy for when I give you small numbers where you can just really quick churn through the numbers in your head and figure out real quick, okay, the greatest common divisor of those is whatever it is. But Euclid's algorithm is an efficient way of calculating the greatest common divisor between numbers that you might not know, like 2,896 and 1,940. Greatest common divisor of those, what might that be? There's no obvious trick for you to go through in your head to say, oh, that's going to be, and plug it in. So we're going to go over Euclid's algorithm, which is going to be how you calculate these things. Now you're going to have to use Euclid's algorithm on your test.
I remember doing this. I think I've done this before. That's where I have. Okay, keep going.
You might have. For some reason, I have a vague memory of teaching it.
Teaching me it?
Yeah. Did we cover this in trig for some reason?
Well, I wasn't in trig, but
Well,
you might have done it in Johnson too.
anyways, so we're going to figure out the algorithm for calculating the greatest common divisor between 2 of those things, and it's actually a relatively efficient algorithm for massive, massive numbers. So once we figure out what the algorithm is, we're going to find out that this algorithm is actually pretty quick for calculating the greatest common divisors between 2 numbers that have 1,000 digits. So I write a 1,000-digit number here, and another 1,000-digit number here, and I want to know the greatest common divisor between those 2 numbers. You can actually figure it out relatively easily. Not by hand and paper. That would still take a long time, but the point is a computer could, which is of practical importance for cybersecurity nowadays. I think we'll get to encryption, how we make information secure on the web. So it's a really easy thing for a computer to do, in other words, is what we're going to prove. So let's start by proving something at the crux of Euclid's algorithm, and then we'll continue from there. So here's what's at the crux of the algorithm. Let A and B be positive integers, or in other words, natural numbers. Well, no, because we don't want 0. Let A and B be positive integers. Have I used this notation before for positive integers?
I think so.
So that's not great. Where was I? C equal A mod B. Then the GCD, this is going to be our pretend function for calculating the greatest common divisor, of A and B is equal to the GCD of B and C. So let me write out a hard example to see what exactly they're saying, and then we'll prove it in general. So let's say that I'm trying to figure out the greatest common divisor between 24 and 18. Okay? So what this is saying is, whatever the GCD between 24 and 18 is the GCD between 18 and 24 mod 18. So the GCD of this is also the GCD of 18 and 24 mod 18. And what's 24 mod 18?
I've got it word on it.
24 divided by 18 has a remainder of
6.
6. Wonderful. 6. Do we need to go over what mod is again in
No,
div?
we got it.
Div, divide, mod, remainder. That's why it's called mod. Remainder.
Okay.
Okay, 6. Someone's listening. 6. So the GCD of these two is also the GCD of these two, which we know that the GCD was 6 to begin with, right?
Yes.
The GCD of those two is 6. GCD of those two is 6.
Okay.
Okay, so that's what the algorithm's saying. It's not the algorithm. That's what the theorem is saying. It's saying the GCD between these two numbers is also between these two numbers. Nice thing about these two numbers, they're smaller. And that's what, you see how 18 and 6 are smaller than 24 and 18?
Oh, I see.
I can't do A mod B and get something bigger than A and B.
Right.
I can't divide and get a remainder bigger than the numbers I
Right.
started with.
Okay.
So this is always making the number smaller. So this pair of numbers is always smaller than these pair of numbers. So Euclid's algorithm is basically doing this over and over again until you get your GCD to pop up. Make sense? So this little theorem is what's at the heart of it. We need to prove that the GCD of two numbers is the same as the GCD of the one number and the mod of the two. So you understand the theorem we're trying to prove?
Yeah.
And hopefully motivated how we're going to make an algorithm out of it. Okay. And like I said, Euclid proved this, so it's actually, he has a geometric proof of it.
How do you prove this geometric?
You represent A as a length and B as a length, and how can I say this right without confusing you more? Geometrically, you're saying I have this length A and this length B. I want to know what is the longest unit I can make so that I can use it to count how long this is and count how long this is. That's the geometric version of the question. Construct a segment here so that this segment goes into this some number of times, some integer number of times, and this segment goes into this some integer number of times, making this segment as big as you can. That's also the GCD. So that's the geometrical thing about it. You could prove that, but this is the number theory version of the same theorem. Almost. This is going to help us do it. Okay. So let's do this proof. All right. So we'll say just going to do D for my variable. Because we've used A, B, and C, right? So let D equal the GCD of A and B. And let E equal the GCD of B and C. Now we're going to do two things. We're going to prove that D is less than or equal to E, and that E is less than or equal to D, and therefore they're the same thing. we're trying to prove that the GCD of this is equal to the GCD of this. We're calling the GCD of this thing D, we're calling the GCD of this thing E. Now we need to show that D is equal to E and we're done. The way we're going to show that D is equal to E is we're going to show D is less than or equal to E and E is less than or equal to D. Therefore they're the same number. You understand the... Okay. So let's do it. 2. Okay. So since D is the GCD of A and B, then D divides A and B, right? Because it's the greatest common divisor, so it is a common divisor of both these things. So, maybe observe that D divides A and D divides B. Trying to think how we're going to tie this together. Because I need to do D also divides B and C, and I'm done. So I need to get D divides C as well. So I know that D divides A, and I know that D divides B. Then let's see. What is C equal to? C is equal to...
A mod B.
Yeah, so it's equal to A mod B, which gives us that A is equal, not A is equal to, that C, it's the remainder. Maybe I'll write to the side how I'm going to do it and then put my actual equation here so I don't lose any algebra. If C is equal to A mod B, then that means A is equal to QB plus C. So we're going to have that C is equal to A minus QB for some Q and Z. You with me? So that's what I'm going to skip to. So since C is equal to A mod B, then we have C is equal to, maybe I'll say, this implies that there exists Q such that C is equal to A minus QB. Good?
Yeah.
Now remember, we know that D divides A and D divides B, so D divides both these things. So that gives us that D divides C. You got that, Lee?
No.
Wait.
D divides A and D divides B, so D divides this difference. Okay. You're going to make me introduce two new integers? Okay.
Oh, I see what you're doing.
So this gives us that there exists, what am I going to use? M and N. And such that C is equal to MD minus QND, which gives us D divides C. How's that? Still done? Okay.
Just why don't you explain it instead of just how you expect it?
I'm just factoring out a D. So.
Where?
Oh, you're factoring out the.
So
Where did you
C
get N?
is, huh?
What?
Oh, are you confused how I went from here to here?
Yeah.
Oh, sorry. I thought you were just confused by my final step. Okay. D divides A. Okay, let me expand here. This gives us that there exists M and N such that, where's this correct work? Such that A is equal to MD and B is equal to ND. Then get rid of this and just rewrite it right here. So C is equal to MD minus QND, which gives us C is equal to D times M minus QN, which gives us D divides C. How's that?
That works. We're good.
Any weird step in there? Nope. Okay. So then, I know that D is a common factor of B and C. So follow the logic of what we did. We said if D is the greatest common divisor of A and B, then it is a common divisor of B and C. Maybe not the greatest, but it is a common divisor of B and C. E is the greatest common divisor of B and C. So for then D is less than or equal to E. D is a common divisor of those two numbers. E is the greatest common divisor of those two numbers. Therefore, D has to be less than or equal to E.
Right.
Follow that logic?
Yeah.
Now we're going to do something very similar, again, to show that E is less than or equal to D. We're going to start with E is the GCD of these two. Therefore, it's a common divisor of these two. Therefore, E is less than or equal to D.
Therefore, D and E are equal.
Right, that's what we're trying to prove ultimately, right?
Okay, yeah.
GCD of this equals GCD of this. So, that handles that part.
That's what should be.
Okay,
We don't even know what E is though.
it's defined right here, sorry. I'm just naming these things.
Oh.
I'm just saying D is the GCD of that, E is the GCD of that. That's my names for these two things. And now I'm going to show that E is equal to D.
Oh. So basically that means E divides B and C.
Yeah, I'm going to show that since E divides...
Right. Okay, I'm following you.
Okay.
Alright, good.
Right. So we know that, so observe, did I hit record?
I did.
I'll take it.
Well, I have no memory of it. Yep, I did. Alright.
That's a Timson brain for you.
Anyways, so observe that E divides B and E divides C, right?
Mm-hmm.
There exists two more. I guess you don't need to do that now that we understand it.
Yeah, I think you guys can follow it now, so we don't need to say that. But E divides B and E divides C, comma, and A is equal to,
A is equal.
yeah, I need to get A in terms of C. And maybe I'll do there exists Q prime to make it different from the Q we did somewhere else. And there exists Q prime such that A is equal to Q prime B plus C. So our definition of C. C is a remainder. C is equal to A mod B.
Right. I remember up there we could still see it. You read.
C is equal to A mod B. That's its definition. So in other words, C is the number that satisfies this, where C is less than or equal to B, but it doesn't matter. The point is, I can write A this way. Right? Then A, well, maybe you're good with this. Then E divides A, you good with that?
Same thing as right there. Right?
Same thing as before. E is a factor of this thing, E is a factor of this thing. Therefore, E divides A, which gives us that E is less than or equal to D, which gives us that E is equal to D. Since E divides both A and B, then E is a common divisor of A and B. D was the greatest common divisor of A and B, so E has to be less than or equal to D. And since D is less than or equal to E and E is less than or equal to D, they're equal. Follow that? Okay. Now we're ready for Euclid's algorithm. How does Euclid's algorithm work? I think the best way to do it, to get a feel for it, is to just flat out see it in action. We're just going to calculate the GCD over and over and over again. We're going to calculate the GCD, get the remainder, and then calculate the GCD with the remainder, get the remainder, calculate GCD with the remainder, get the remainder, and do that over and over again until we get the GCD. Sorry, that wasn't a good way to say it. Seeing it in action, I think, will help. So let me just find two numbers that they already have. So the GCD of 689 and 234. So let's just see it next. We're trying to find the GCD of 689 and 234. Did I write that right? 234. Yeah. Okay. So we're trying to find the GCD of these two things. And we know that the GCD of these two things is equal to the GCD of this thing with the mod of these two things.
Right, yeah.
Okay? So I'm going to rewrite this 689. I need to figure out what their mod is. What is this mod this? The way I'm going to do that is I'm going to write it in this form. That's equal to some number. How many times does this go to this?
2.
1 is equal
2. If you do that, if you do the 34 3 times, you're going to get more than 100. So it can only go in twice. So it's going to be 2 times 2, 3, 4 plus, what's the other part going to be? 68, so that's 21, 221. Did I do that right?
Yep.
2 times 34 is 68 plus 21 is 89. And obviously the 200s come up to 600. Good with that? So the GCD of this thing is also equal to the GCD of 234 and 221. Repeat and repeat. So 234 is equal to how many? 1, 221, plus what?
13.
13. And 13 is prime. So we know that we're done.
So it's always, you're always done when it's prime?
Now, let's continue to see what happens next. It's when you get a 0 for the remainder that you're done. But that's going to happen when we continue with this. So let's pretend we didn't know 13 was prime and now we're done. But we are. Anyways. Oh, no we're not. We're not done.
Sorry. Alright.
My bad. Ignore what I said. So now we know whatever this is, it's also equal to the GCD of 2, 2, 1, and 13. It can still just be 1 as their greatest common divisor. So 2, 2, 1 is equal to how many 13s? No, it can't be 20.
19, 18.
Might be 17. What's 17 times this? 17 and 13 gives us what?
21.
So that's going to be 1, 2. Oh, what am I doing?
That's right.
What? I have not written this out in so long. I just want to do it in my head and add it together. 13 times 7
Yeah, it's a.
is 1.
You did
Why do
the
I
math.
want to write the
Hey,
2?
Hey,
Huh?
you did
It's
the math. It's 17.
Does it come out exactly though?
Yeah.
What is going on in my brain right now?
Right, so there's a remainder of 0.
3 times 17. That's what I keep doing wrong. 3 times 17. Good, Judy.
What the
3 times 7, 1, 2. It's been a long time since I've written it out like this. And that comes out to 1, 2, 2, 1. Comes out exactly. So 13 times 17. 17 13s plus 0. And once you get a plus 0, you know that you're done.
Right, obviously.
If there's a remainder of 0 between these two numbers, then that means 13 went into it an even number of times.
So what's the GCD then?
13.
How interesting.
I mean, you could continue it for a sanity check if you wanted. GCD of 13 and 0. If you continue to the next line. 0 has every divisor. Every number is a divisor of 0. So what's the biggest divisor of 13 itself? So there's a sanity check if you want to continue with it. But that's Euclid's algorithm. So we just performed it. You're going to have to do this on your test. So let's do another example.
You're going to have to do this or prove it?
I'm going to give you two big numbers. and you're going to calculate their greatest common divisor by hand. No calculator.
What? Okay.
I'm going to give you two big numbers.
No, I'm.
So let's do another example. Let's see, they got 13. I don't know. We can just pick two numbers. Let me come up with a contrived example real quick. So let's do it between 294 and 119. Maybe that's going to come out too quickly. I want one that takes a few steps. Do they give another example?
Do in the thousands.
Yeah. But even if you do it in the thousands, you might accidentally pick so it comes out way too fast. Come on. All right, we'll just pick something and see what comes out. Give me two numbers. 1,000 what?
1370.
1,1370.
Saying 1,370.
1,370. Okay, and what?
Do 1,100.
507.
Well, the closer they are together, the longer it's going to take.
No, the quicker it's gonna happen.
Yeah.
Yeah, because your remainder's gonna get really small really quick.
Oh.
So let's do it. Okay, so doing Euclid's algorithm, 1370 is equal to, how many of those are we gonna get? Two of those. 2527. And then what's that going to be? So multiplying this out real quick, we're going to get 4501. 1054, so that's going to be 216. Did I do that right? Oh, 316.
No, it'll be 3, yeah.
316. Do that right?
Yeah.
Okay. So now we need the GCD of 527. It's going to be 1316 plus what's going to be for that? 211. And then 316 is equal to 211 plus 115. No, 105. I mean. Right? 211 is equal to 105 plus 1. So the GCD is 1. I wonder if 527 is prime. No, it's 31 times 17. But since neither 31 nor 17 go into that. Huh?
How do you figure that out?
I guessed.
Okay.
I mean, you can make reasonable guesses about what we're going to do there. So, there it is in action again. So that's Euclid's algorithm. You feel like you understand it well enough that you can do it? You want to do another example?
Yeah.
All right.
It's a couple more.
Well, you're going to do it on your homework too. So it's not like this is all the practice with it you're going to get. Got some numbers?
Anything, doesn't matter.
Anything isn't a number.
1738 and 236.
Okay. use my calculator to hurry and get these numbers.
So you're gonna let us use it on the test, right?
No.
That's bull.
I know. Nothing wrong with some good old baloney. So that's 7, 2, 3, 6.
I think most time we decide the option is just find the greatest common divisor.
But we're going to go through the steps. Plus 86, that's what that comes out to. So then what do we do?
236 equals 86 times something.
So 236 is equal to how many 86s are we going to have?
Probably we get 4 and a half or 3.
We don't even get 3, we only get 2 of them.
Only get 2?
Yep.
14 and 2.
It's going to be 2 86s plus, let's give you the remainder, I'll ratio. 64.
You want us?
What are the odds? Continue. 86 is equal to 164. By the way, you'll notice how I keep writing these numbers in parentheses the way I do. We're going to use eventually an algorithm called extended Euclids, which is kind of like you do Euclid's algorithm and then do a reverse algorithm again to give you 2 very important numbers. So this is good practice to keep track of which numbers which. To keep track of it was 164, not 64 ones. Now it was obvious which one of these was our Q and which one of these was our B because of doing the problem. The numbers can get close enough together that you'll lose track of which was which. And it's important to keep track of which was your quotient and which was what you were dividing by. So as a matter of convention, I do it like that because it becomes important later, as we'll see. Anyways, plus what?
22.
Good. How many?
2.
2. Plus what? 20. So here's a case where it might not have been obvious which one was
Yeah.
the quotient and which one was what you're dividing by. Anyways, and there we have it. So the greatest common divisor of them was
2.
2.
Wait, what?
It seems like if you randomly choose 2 numbers, the odds are that their greatest common divisor is going to be really small.
I'd have to think about that for a bit. Not being relatively prime, or whatever those are. We'll get into that more. Okay, anyways, there's Euclid's algorithm. I don't know if there's much to be gained by proving that Euclid's algorithm works. I think once you understand this here, you understand how Euclid's algorithm does work.
Isn't that basically what we did over there?
We did that a whole bunch of times. And so the way that they prove Euclid's algorithm works is they do assume by way of contradiction that it doesn't work in. Because all we've done is shown that it works with very particular numbers. We didn't show it works in general. But we applied that theorem over and over again. So I don't think you get that much insight from proving that it works. You can read the book's proof that it does work. But I think when you understand this theorem, you have a good enough understanding of how Euclid's algorithm works. So I'm not going to bother going over that, unless you guys are opposed. Well, you sound infuriated, so guess I'll continue. Jeez, it is hot in here. 73 degrees. Crazy calculus students.
You left it at 68.
68 is a wonderful temperature. Mid to high 60s. 70 is pushing it. And 73 is just insanity. Okay, So the next thing that we want to talk about and do a little bit of proving for is how fast this algorithm finds the greatest common divisor. Like, even if you were terribly unlucky and you picked two numbers that it happened to take a lot of steps for, what's the most steps it could possibly take?
Is there a max?
Yeah. So this is a little bit of introduction to the type of analysis you would do in a computer science degree. We're very interested in worst case scenario, how an algorithm will perform. Because you don't want to accidentally spin off an algorithm that's never going to terminate, for example. That's bad.
Right.
Because then your computer's in an infinite loop and you don't know, is it in an infinite loop? Did I screw something up? Did it crash? What's going on? So, how long it takes, worst case scenario, to compute an algorithm is the next thing that we're interested in. So, for example, if we wrote two 1,000 digit numbers up there, how many times would we have to go through the algorithm, worst case, to get the GCD? And that's what we're going to figure out. So a little side proposition that we're going to use before we do a calculation. Prove. Let A, B, and Z with A greater than or equal to B greater than 0 and let C equal A mod B then C is less than half of A.
Is it 7? 7 times. I mean, I'm not this, but would it be 7 times to terminate?
I don't understand what you're saying.
Saying how many times would you have to run through before it ends? Would it be 7 times?
It depends on the size of the numbers. Bigger
saying
numbers run more times.
Worse, where do you? Okay. Okay.
I'm saying if you have a two-digit number, so if A and B, if I know that A and B are two-digit numbers, maybe at most it has to run 3 times. But if A and B are 20-digit numbers, maybe it has to run at most 20 times. Is it like, does it have to run like 3 times per digit maybe or something like that? What does it have to do?
Okay.
So let's figure it out. So this right here should be pretty intuitive real quick. So I have A is greater than or equal to B, and I define C to be the remainder after the division. C has to be less than half of A.
Why?
Well, we'll prove it, but the intuition is you can't take A divided by a number B and end up with a remainder more than half your number. The smallest integer you can divide by
Is
to get a remainder is 2. If you divide by 1, you get the number. If you divide by 2,
1/10 of each half.
we're saying that backwards. The biggest number you can divide by is half of C.
Yeah.
So the smallest you can make the quotient is 2. And so the biggest your remainder, for example, let's come with a convoluted one. If I do 149 divided by 50, or mod 50, I mean, then that's going to have a remainder of 49. Or maybe a better example would have been 99. Then that's going to have a remainder of 49, which is slightly less than half of this.
Yeah.
But I'm never going to be able to make the remainder more than half of this. Because getting this as close to half of this as I can maximizes the remainder. I don't know. Trying to make intuitive sense here, we'll actually prove it. And we're going to need to handle 2 cases here. We're going to consider the case where A is more than twice as big as B, and A is less than twice as big as B.
Why do we do that?
we're handling, well, trying to make this make more intuitive sense. So here's A. If B is close to the same size as A, then obviously the remainder is less than A, or is less than half of A, right?
Yeah.
Then the other case we're going to handle is basically if B is much smaller. So it's possible for its remainder, just looking at the picture, it's possible for its remainder to be more than half of A. But it turns out that's not going to be the case anyways. Sorry, that might not be the greatest intuition for why we choose the two. In short, the reason we're choosing the two is because we're talking about A halves. We'll just go through the proof.
Yeah.
I don't know how to make it more intuitive than that without, yeah, I don't know. For some reason, it just feels to me. All right. There we go. Okay, so they want to do case 1, A is less than 2B first. So, assume A is less than 2B. And let's see what we're trying to get. We're trying to get that C is less than A halves, so let's write what we know that C is. We know that C is equal to A minus QB, right?
Oh,
There exists some Q such that A is equal to QB plus C, which gives us C is equal to A minus QB, is what I'm thinking. Let's think. I'm trying to get C is less than A halves. I also know, sorry, I'm just kind of thinking out loud here. I also know that 0 is less than or equal to C is less than B, because C is the remainder, right?
are you following the book or no?
No.
How come?
Just see if it pops in my head. Usually don't need to follow too closely. We know that 2b is greater than a is greater than 0, and that a minus b is greater than or equal to 0. Maybe that's inequality I wanted. So since a is greater than or equal to b, that means a minus b is greater than or equal to 0. So we know a minus b is greater than or equal to 0, and from this, we know that a minus 2b is less than 0. A minus b is greater than or equal to 0, but a minus 2b is less than 0, since 2b is a bigger number than a. Okay, that makes sense. Hence the quotient when a is divided by b is 1. Hence the quotient when a is divided by b is 1. A minus b is greater than or equal to 0. But if you get all the way to 2, you got something less than 0. So the most b's I can go into a is 1.
Right, okay.
Okay, so that gives us that a is equal to exactly 1b plus c.
Right, okay.
divisor so far.
Wait, how did you get that last one? What's the thinking behind it?
Okay. The thinking, remember A is greater than or equal to B. We're saying how many B's go into A?
So it's
We know that if we take away one B from A, we've still got a positive number. So at least one B can go in. But if we take away two B's from A, we get a negative number. So we can't take away two. So at most one B goes into A. So this quotient is 1. And then C we already know is the remainder. So A is equal to,
so it's like A divided by B. That's what we're doing.
that's what we're doing? Yeah.
A mod B, yeah.
Okay. Okay.
So now we know exactly what C is. Then C is equal to A minus B. Still not seeing polygenes. C is equal to A minus B. Now we can rewrite A is less than 2B and B is greater than A halves. So A minus B, oh sorry,
That doesn't make sense.
A is less than 2B can be rewritten as A halves is less than B,
Right.
right?
Okay.
Oh, yeah.
So are you trying to show now that C is greater than B? Is that the next step?
We're ultimately trying to get to here.
Right.
So this is a substitution I need to make here.
So what I'm saying is, if you can show that C is greater than B, then you can show that C is greater than A over 2.
That's where we're going. Okay, now I see that that's substitution. So here's where we were going with that. A halves is less than B, right? So remember, this is a positive number. This is a positive number.
Oh, I see.
So if C is equal to the difference of these two things, then so if C is equal to the difference of these two things, it's going to be less than the number you get when you pick a smaller number than B here. Take away something less than B makes this whole number
B
bigger.
is not greater. Oh, yes, it is, because
B
A
is
minus
bigger than
B
A
is
halves.
less than 1/2. That makes sense.
So B is greater than A halves.
Yeah, yeah,
So we're subtracting a smaller number here than we were subtracting here.
Right.
So this number here is a smaller number than this number. This number is bigger than this number. We
Right.
took away a smaller
Right.
portion,
Makes sense.
so we have a bigger number. And evaluate, that gives you A halves.
That gives you
Therefore,
halves.
A minus B
Ow.
is A minus A halves?
You guys are gonna hurt my head now.
Oh.
If you have a pizza and you subtract half of a pizza,
My bad.
you have half of a pizza. Okay, now let's do it the other way. Assume A is greater than or equal to 2B. Right?
What's you we're doing?
So we handled this case. If A is less than 2B,
Oh, right.
C is less than A halves. Now, if A is greater than or equal to 2B,
So just a question, could we, like theoretically, we could have done any number, I mean, that, not 2B, it could have been 3B, that is my point, we would show different intervals. Does that even make sense?
No, it has to be
So in
two,
your
because
proof, you're showing if it's greater than or equal to and less than or equal to, then it's true. But could we have done it in 3 sections or 4 sections rather than 2?
broken up into 3 cases,
Yeah.
it would have been hard.
I know, but like, we could have, that's my question.
It's true in all those cases, so technically you should be able to prove it in all those cases. I mean, in reality, your proof might reduce to doing something exactly like what we have here.
I see what, I'm not saying that's what we should do, I'm just trying to wrap my head around why we chose, why we are doing it this way. Anyway, that's the reason, right? Then it shows it's true for all those numbers. Doesn't matter what, my point is, doesn't matter what we split it up, you're gonna prove it for all those numbers.
So in this, here's the way to think about it. In this case, B goes into A exactly once. So we've got two cases. We've got the case, here's A, and B goes into it exactly once. Can't go into it more than one time. In which case, obviously, the remainder is less than half. The other case that we're doing is B can go into it more than once. But if it can go into it more than once, then B is less than half this thing, and the remainder has to be less than B, so once again, it's less than A halves. Let me finish this proof, and then we'll come back to the picture, because this proof is almost done. So assume A is greater than or equal to 2B. This gives us A halves is greater than B. Greater than or equal to B, right? Divide both sides by 2. And we already know that B has to be greater than C. So it's the remainder. The remainder can't be bigger than what you're dividing by.
Oh, right.
I can't take a number, divide by 10, and get a remainder of more than 10. I can't take a number, divide by B, and get a number bigger than B. Has to be smaller. Okay, so we have two cases here. B only goes into A once, in which case the space for the remainder is already less than half of A.
Right.
Or B goes into A more than once, which means B can't be more than half of A.
Oh, right.
So the remainder can't be more than half of A.
We said,
Okay, are you good with this case?
yeah.
So now we're talking about this case.
Okay.
B is less than or equal to half of A.
Okay.
And the remainder is less than B.
Oh, okay.
So the remainder has to be less than half of A.
Okay.
So those are the two cases. B goes into it exactly once, in which case there's less space for a remainder than half of A. B goes into it more than once, which means B could have been at most half of A, and so the remainder has to again be less than half of A. And those are the two cases.
Okay.
Okay? So that's the end of the proof. But now let's write out what's happening when you have two numbers A and B in each step of the algorithm. So if I start out with the GCD of A and B, then at most in the next step I'm going to be looking at the GCD of B and a number that is at most A halves. It's going to be smaller than A halves. C, the number here. You understand what I'm saying? I'm saying as we run through Euclid's algorithm.
Why do we choose A halves?
We know that C is going to be less than A halves.
Okay.
So calculate the GCD between these two. When you're doing Euclid's algorithm, the next thing you have here is a C, right? C, the mod of A and B. Right? Whatever this number is, it's going to be at most A halves. I'm showing you how the numbers decrease in each increment of the algorithm.
So it's less than.
Well, let's continue.
Okay.
So
Yeah, if that was the case, it would be C.
GCD now, if we go to the next step here, what are we going to have? This is going to be A halves at most, and this is going to be B halves at most.
Right. Oh.
So in every two steps of the algorithm, the numbers will at most be half of what they were before.
Yeah.
Worst case scenario.
So how do you know when you're done?
When one of them gets to 0.
How can they get 0 if it's decreasing by
When one of them gets less than 1.
less
What
than,
integer is less than 1?
or equal to, right?
What integer is less than 1?
There's not. My point is so it's less.
There is an integer less than 1. 0.
Oh.
So if I get this less than 0, and I'm guaranteed that that number, if I get this less than 1, and I'm guaranteed that the number here is smaller than this one, then it has to be 0. The algorithm's done when this is 0. Is that confusing?
No.
Let's do an example one more time. And then we'll see what I talked about in action.
Except like I swear they weren't
So,
less, I swear they weren't half of each other.
Right, so let's do it one more time. Pick numbers.
okay. Well, I just had a question, which is there ever going to be a case where it's going to come out as that maximum number?
No, it can't be exactly half. It has to be less than. C has to be less than 8 halves.
Right. Okay, that's what I was thinking.
So it's an upper bound.
Is there ever going to be a case where it's exactly 1 less than that number?
Okay, so the next one down
This
will be
this might not be an
halves.
integer. In fact, it's very quickly not going to be an integer.
Right.
So it won't be 1 less because that's not an integer. It's just an upper bound. That's all we're saying. Is at most, these numbers have to be half of these numbers. They have to have gone at least half as big. They're going to be less than half of what they started out as, but we're saying worst case scenario.
So you're saying if you were to find the least common divisor of 2 really big numbers, then you could run through it maximum of less than half times.
Right, so I'm saying, for example, let's see.
Less than half of,
So I'm saying you have the number 1024 and any other number here,
okay,
862. I'm saying the most times that this thing could possibly run is 11 times, because this is 2 to the 10. This number right here is 2 to the 10.
okay,
Oh, sorry, the most you can run is 20 times. Because every increment, we're going to divide by 2. Every 2 increments. Let's just see numbers, and then we'll do whatever. So, pick 2 numbers, and we'll see exactly what I'm talking about in action.
okay,
It's not a number.
That should be 10 times.
24,
right?
30.
10 times what? 2, 4, 3? 2, 3?
Sure.
Alright, barely less than. And give me another one?
3,600.
Well, make it less than this one, so
Oh, right.
we don't get confused with days and weeks.
1,200. 700.
900.
700. It doesn't matter.
Okay.
Take too long. Alright, so let's do it. So we're looking for the GCD of 1023 and 129.
Right.
So 1023 is equal to, how many is that going to be?
8.
I think it's going to be 7.
Always one less than what I said.
Well, chances are you can at least get within one of that. 1023 divided by 129, 7. Yeah. So 7 times.
It was 8. Almost. 7.9.
Not 8, exactly. Minus 7, oops, not plus, times. Plus 120. Okay, so now we're saying that's the same as the GCD of 129 and 120. Notice this is less than half of that.
Why did you switch your parentheses over there? That's so confusing.
Oh, sorry. You're right. That's not typically what I do. It's because I was using the calculator as I was going. Okay, so now we got 129 is equal to 120 plus 9. So now we're looking for the GCD of 120 and 9. Notice both these numbers are less than half of these numbers. So we're guaranteed in 2 increments of the cycle, calculating it twice, the numbers that we have here are going to be less than half of the numbers that we have here. That's guaranteed.
So that's all that we proved.
That's all that we proved. So worst case scenario,
So that sounds so much more simple than what I was thinking at the beginning.
worst case scenario, this number is roughly 500, and this number is roughly 60. Worst case scenario.
So how do you know how many times you're going to have to run through it?
Worst case. We'll calculate that real quick.
Is it the smaller number or is it the larger of the two?
Well, it matters what this b is, because it's how long it takes b to get to 0. Actually, that's not true, because So it's until one of them gets to 0.
Right. So how do you know which one will get there faster?
Worst case scenario, they're going to get there at the same time.
So it's the worst. Okay.
You're trying to think about, you're overthinking worst case. It's like my calculus students. Sometimes you have to prove that something exists.
Alright.
And that's all you have to do, is prove that something exists. And these guys work so hard trying to find the exact thing. We just had to prove it existed. You didn't need to find what exactly that was. This is worst case. You're not saying, well, worst case when A is bigger or when B is bigger or when da, da, da. No, just worst case. Don't try putting other conditions on there. If B goes to 0, we're done.
So my question is, when you get a number, like you choose two random numbers like that,
Just order them.
worst case scenario, how do you know how many times that's going to take? Is it going to
How many times it takes dividing B by 2 to make it less than 1? How many times do you have to divide B by 2 to get less than 1? Is the answer.
So that answer would be, what, 64, 65?
Well, let's calculate it in an insane example. You half it every time. That's what log base 2 is, right?
What does that have to do with this though?
That's exactly what we're going to be talking, what we're calculating. So let's do it with an absolutely massive number now and see at most, worst case, how many times it would take. So let's say, now we just he choose to use. Oh, he does it in general, and then he does a specific case. But the point is, so far, in 2 steps, we have the numbers. Right?
Mm-hmm.
So every 2 steps, we're guaranteed to have the numbers. So, when we get, well, how's it
That
going?
would be 7 for this. Doggy.
7. Oh, because you're thinking about that.
129
7.
is B, right?
129 is B.
Yeah.
So
So I
let's
divided
think.
that by 2, by 2, by 2, by 2, by 2. And it was 7 times. Until it was 1.
Oh,
You see what she's saying?
I see what you're saying.
Is that right?
128 is 2 to the 7, right? No, 2 to the 6. So 2 to the 7 is 256. So yes, that's the first time it gets over. So 7. That's correct.
Yeah.
Times 2.
Right.
So 14 steps, worst case.
Wait, times 2, why? Oh,
It
right,
takes
right, right.
2 cycles to have the number,
Right.
right?
So times 2, that makes sense.
So let's write this generically. So after t cycles, what are we going to have?
What do you mean?
How big is this number going to be after t cycles? So we know after 2 cycles it's a halves. We keep doing this t times.
So it'd be a over 2t?
So we have it every 2. He's saying 2 to the negative t times a, 2 to the negative t times b. And I feel like that's going to be off by a factor of 2. So let's make sense of that. After t cycles, after 2 cycles, that's a 4th. No, so it should be to the 1/2 t. So why does he do to the negative t? Since every 2 steps increases the number by more than a factor of 2, we know that after 2 t steps, after 2 t steps, and this is what it is. So after 2 t steps, here's what the numbers are going to be. Now that makes sense. So let's make sense of this real quick. After 2 steps, what are the numbers going to be? A halves and B halves. So after 2t, if t is 1, then plug in 1 here. 2 to the negative 1 is 1/2. 2 to the negative 1 is. Okay, after 4 steps, that's when t is 2. Plug in 2 for t, you get 1/4, 1/4. So after 2 t steps, this is what the numbers are going to be.
What about why are we finding 2t rather than 1t?
So you don't have 1/2 up here. So it's either after 2 t steps it's this, or after t steps you'd have to put 1/2 in your exponent. So I guess he thinks it's simpler to keep your exponents whole numbers. That make sense?
No.
It
So
makes
really,
no
what
difference.
You're saying that bottom one could be that third one right there. Like it doesn't matter. And 2t could be
Pick
that
how
second.
many cycles you want it to go.
Right.
100. If you want to go 100 cycles, t is going to be 50. Plug in 50 here, that's what you're going to get.
What do you mean that's where you're gonna get? For what?
For the
very
values.
last step?
For the size of A and the size of B. For what they could be at most. Look, after 8 cycles, how big is A going to be? Or how big is this number going to be?
I don't know.
After 2 cycles, it's half of A. After 4 cycles, it's a fourth of A. After 6 cycles, it's an eighth of A. After 8 cycles, it's a 16th of A.
Right.
So after 8 cycles, if this is 8, t is 4. Here's your number of cycles. Your number of cycles n, we're going to write as 2t. So pick your number of cycles. 8.
Right.
What's the t that gives you 8? 4. Plug in 4 here and here, and there's your numbers. 2 to the negative 4 is 1/16. Maybe, let's write it this way. Maybe the exponents are being worked for you guys. A over 2 to the t.
No, that's not the issue.
B over 2 to the t.
Right.
Is that clearing it up?
I'm just saying, is that the very last step?
Well, we're just saying in general.
That doesn't make sense.
We're saying after how many cycles? After 2 t cycles, this number can be at most A divided by t over 2. And this number can be at most B divided by 2 to the t. What did I say?
I'm
I said
confused.
something weird. I didn't say it right too.
What line is that though? Is that the very last
That's the
line?
nth line. It's in general. It's just like if I say f of x equals x squared. I'm saying x goes to x squared. And you're saying, wait a second, is that 3?
Listen.
Is that 6 goes to 6 squared?
Stop. Are you saying that you can get that by that? Okay, so say you have 4 up there. You have 4.
You'd have 4 iterations.
Okay.
So
and
t
then
is
you
2.
get the 5th one, and then you keep going.
Oh, you can do that if you want, but we're just saying after, for example, after 50 cycles, how small of numbers are you going to have? A
It's basically just
over
check
2 to the
the
25, B over 2 to the 25. So,
Oh, I see.
yeah, so a quick practical example, it's exactly what you did
So
already.
it's not like you do it after you've already done all the steps.
We're just doing some analysis on worst case, how big these numbers will be. Right? And we know that we can stop when b over 2t is less than 1. If b over 2t is less than 1, then we know that we're done.
Right.
Does that make sense? So we know that we're done when b is less than 2 to the t.
Right.
Which will happen when log base 2 of b is less than t. Take log base 2 on both sides.
What's log? No,
You don't know log?
no, I do not.
Okay.
It's if I remember. Yeah. Well, we learned it like 2 weeks ago, so.
We did?
Well, in college algebra, sorry.
Oh.
If b is equal to a to the x,
Then,
is that the right way to think about it?
yeah, it is.
And
X equals,
log base a of b is equal to x.
yeah.
If you see that log base a of b equals x, that means a to the power of x equals b. The log is the inverse of the exponential. It undoes it. The same way that subtraction is the inverse of addition, dividing is the inverse of multiplication, log is the inverse of exponents. So, if I take log base 2 of 2 to the 100, that's equal to 100.
Oh. Wait, no, it's not.
2 to the 100 is equal to 2 to the 100.
I'm surprised.
Wait, what?
A to the x equals b. 2 to the 100 equals 2 to the 100. Make sense? So that's what I did over here. I had this, and I take the log base 2 of both sides. Log base 2 of b is just that, but log base 2 of 2 to the t is just t. Oh, they went a long way of doing it. But in other words, so half the number of cycles is going to be more than this number. So you calculate this number, take the integer bigger than it, times it by 2. That's at most how many cycles it's going to take. So let's do a quick calculation now. Give me any massive number you want.
Any massive number.
Any massive number you want.
7,632,000.
7,600,000 of what?
32,027.
And another massive number? Has to be smaller than that.
327.
Oh, you made that small.
Oh, sorry, yeah, that's a small number.
1,000.
Yeah.
So, if we were dealing with these two numbers, what is worst case scenario? How many times our algorithm is going to run? It's going to be log base 2 of this times 2 of b times 2.
And it'll be less than that.
And it'll be less than that. So, where's my log button?
On the left. Should be on your left side. Oh, no, you have to go with math. It depends on your calculator, but there's log base 10 there, you have to go to your
Well, I
math button to get the log.
figured it out with log base 10 as well. I just don't see it.
It's not on your.
It's on there somewhere, I'm just not seeing it. You never use the log button. So just do a quick calculation. Log base 2 of 327,526. Dun 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 dun. And the answer is 18.3, so 36 times is the most it would have to run doing this.
Less than 36 times.
Less than 36 times.
So the minimum is 35, probably.
Right? 36 is an upper bound.
That's what I meant, maximum.
36 is an upper bound. You don't need to start thinking through, but could you also say 35? You're overthinking it. 36 is good enough. So now let's do insane for a second. Let's think about a 1,000 digit number. Let's say that b is a 1,000 digit number. We don't care what a is. A is bigger than b. But let's say that b is a 1,000 digit number.
Okay.
So b is roughly 10 to the 1,000. Has 1,000 digits in it.
Alright.
So worst case, it's going to be log base 2 of this thing.
Equals 2,000. Got
Huh?
2,000.
2,000?
Sure it is.
It's gonna be more like
2, right?
3,500-ish. So, you don't know your log rules,
Now
I
I'm
guess.
confused.
This is the same thing as 1,000
Right,
log base 2 of 10.
right.
And log base 2 of 10. 2 to the 3 gets us 16, or gets us 8. So it's more than 3, because we gotta get to 10. But 2 to the 4 gets us 16, so it's less than 4. So it's between 3 and 4. So we'll say it's roughly 3.5. So it's gonna be roughly 3.5 times 1,000 is 3,500. So if you have just an absolutely massive number,
You get a pretty good
1,000
percentage.
digits in it, you can figure it out in 3,500 steps.
Great.
Sounds rough for you, but that's really simple for you. Computer. A computer churning away 3,500 times is not a big deal.
How quick can a computer do that?
Well, that depends on the computer.
I don't know, an average one? Just do a regular.
It's
like
nothing. 1,000 cycles, 3,500 cycles is nothing. You might notice it stall for a second if you're printing out your outputs as you go, for what it does. If you're not printing out your outputs and you just print out your final result, I doubt you would notice a lag. Cool. Anyways, so, yeah. Relatively quick algorithm for finding the greatest common divisor of two numbers. We spent a bit of time on that. So, continuing. Okay, here's the important one that we're going to be using a bunch after this. Let's get some space. This pink's kind of dying on me, isn't it? See if this screen's showing up okay. Can you see that okay?
I don't know if you can see it on the camera, but I can see it fine.
Yeah, it's kind of hard to see on the camera. Can I see it better than the purple to the right? No. What's that?
Already,
Yeah.
should have taken a picture of the word.
Huh?
I should have taken a picture of the word.
Wait, so how do you calculate it if B is bigger than A?
Spot number. The GCD of B and A is the GCD of A and B. Okay. Theorem. A and B be integers where or not both 0 then the smallest positive integers of the form ax plus by where x and y are integers space seems really weird and pointless. Seems kind of like, why would we care about this? But turns out very useful. We can come up over and over again. And the way that we're going to find these two numbers that the theorem's talking about is with extended euclids. I don't want to write out that table, so just open your books real quick to 262. They have a table on there where they're demonstrating this to you with just a ton of examples so that you can see it in action. So, in this particular example, they've chosen A to be 30 and B to be 24. And they're writing the chart of all the integers you can pick for x and y. And looking at the sum of those, they only did between -4 and 4. Now what they're after is, what are the integers that you can pick for x and y that give you a minimum value, a minimum positive value? Are you reading the table okay?
I don't read an example.
Okay, so A is 30, B is 24. And then each value on the table, so the top left-hand value, -216, that's -4 times 30 plus -4 times 24.
Oh, okay.
So that 6 value that they have right there, that's 130 plus -1 24s. So you see, are you reading the chart okay now?
I get what the chart's saying.
Okay.
I'm trying to understand what we're trying to prove.
Right, you need to understand the chart and then come back to what this is saying. So, here's what, notice that 6, by the way, that highlighted number, that's the smallest positive number on that chart.
Okay.
And if you would extend the chart off to infinity in both directions, with x's and y's, 6 would still be the smallest positive number on there, right? The numbers are blowing up on the sides, that's why he shows it like that. So here's what this is saying. Notice that 6 is a GCD. So he's saying let a and b be integers not equal 0. Then the smallest positive integer of the form, ax plus by, the smallest integer I can get by plugging in x's and y's to this, is the GCD.
Okay.
So it's another way that you could guess at calculating the GCD.
X and Y can be the same then.
X and y can be the same, x and y can be different. X and y are just two integers.
Well, to make it the smallest, they would be the same.
No, not necessarily.
Oh, yeah.
For example, let's see what we know. Let's pick two that we can figure it out real quick. So let's say that A was 10 and B was 12. We know that the GCD of those is 2, right? So we know that this has to add to 2. How do we get this to add to 2? We do -1 of these and we do 1 of these. So they're not the same number. Of course, maybe that's what you meant by same, except for one positive, one negative.
That's not what I meant, but yeah.
But-
I see.
So, if we were to pick any other integers in these two positions, we would only make this, we couldn't find we couldn't make this generate a smaller positive integer than 2, the GCD. That's the smallest integer that you'll get here. That make sense?
Mm-hmm.
This is really weird, but this is like the second most important theorem that we're going to be using for number theory. The first more important was, if you have two integers a and b, you can write it in the form a equal to qb plus r, where
Q and R are unique.
q and r are unique and r is between b and 0. This is the next most important probably for the rest of this chapter. So make sure it makes sense. It's kind of weird. You understand intuitively what it's saying? Proving it's weird, but just make sure you understand what it's saying. maybe we'll take a break there, and when we come back, we'll tackle this theorem.
Okay. Oh, this is a short chapter.
Huh?
Short chapter.
Yeah, but this theorem, I'm worried that understanding it's gonna take the rest of class.
Do we have anything else to talk about after this theorem?
I don't think so. Just seeing it in action, seeing it in euclids. Looks like there's a couple more things, quick things.
So the greatest common divider is the very last b that you get?
When you have 0, and then you also have the greatest common divisor.
So right here, I have this over, it's this number right here, right?
So 185 equals 5 times 37 plus
Yeah.
0.
Ignore that. This
Then
would be
yeah,
the very last one,
37
right?
would have been your
Greatest common.
GCD.
Okay.
Ready to continue? Okay. So, proving this theorem about the smallest positive number you're generating of this form being the GCD of A and B. That's what we're trying to prove. Take the smallest number of this form that you can possibly get, the smallest positive number of this form that you can get. That number is the GCD of A and B. Good? Okay. So we're going to start out with let D be all the integers you can make of this form. D is a set of all these integers, and we only care about the ones greater than 0. So on that table that you had, we're ignoring all the cases that came out to 0 or negative numbers. So now we're just left with positive numbers of this form. Good? You freezing?
I don't know, I just got cold for some reason. I'm okay. I'm warming up.
Turn back on the heat.
No, I'm warming up. Sorry. I have blood on me.
69. Anyways. So D is a set of all the integers we can make this way. Plugging in any numbers you want for x and y. We only care about the cases that generate a positive number though, right? So we're going to argue that the least element of D is the GCD of A and B. The smallest thing in this set is the GCD of A and B is what we're arguing. So first we need to argue that this set isn't empty, and then we're going to take its least element by the well-ordering principle and show that that least element is the GCD. With me on that?
Well, isn't it? Well, I mean, it has to be the GCD. Just by definition, doesn't it?
The number I get of the form, the smallest number I can get of the form ax plus by has to be the GCD of A and B? That is not obvious to my intuition at all.
It feels like because they divide that number, don't they?
No.
Oh, no, they don't.
The sum of this number is the GCD.
Okay.
Remember, the GCD is what this sum evaluates to. That's what we're saying. Right? On the table, the smallest positive number you got from the sum was 6. Good? Okay. So, we're making D the set of all the possible values we can get here, limiting ourselves to positive cases. First thing we're going to show is that D is not equal. So, to show that D is not equal, observe that if we let x equal A and y equal B, we get A squared plus B squared, which is a number greater than 0. Because A and B are not both 0. So it can't be 0. In other words, there are at least 2 integers I can pick for x and y, such that this value is positive. Pick x equal to A and y equal to B. Okay, now this sum is positive. So there's at least one number in D.
So what's with the A squared and B squared then?
This is guaranteed to be a positive number.
Yeah.
So it's guaranteed to be in the
Oh,
set.
you're just showing it's not empty. Oh.
I'm just showing D is not empty.
Okay.
Okay, so we know that there's at least one element in D.
So you could have shown that in a bunch of ways then.
Yep, infinite ways to show that. Good?
Yeah.
Alright. So then D contains a least element, called little d. Little d is the least element of big D.
Why are we using D this time?
Divisors.
Okay. It just seems like we usually use X.
Okay. So, D is the least element of this set. Now we need to show that D is equal to the GCD of A and B. And we're done. Right? Still playing catch up?
I'm confused on what you wrote up there on this line. You said, then the smallest positive integers of the 4, AX must be 1.
Of the form. Thank you.
Sorry.
No, it's a good catch. Hey, that's just a mark for something. So good? Okay. So we're trying to show that D is equal to the GCD of A and B. How are we going to show this? We're going to show, first of all, that D divides A. Then we're going to show that D divides B. And then we're going to show that for any divisor of A and B, D is greater than or equal to it. So I'm showing D is a divisor of A and B. And then I'm going to show it's greater than or equal to any divisor of A and B. Therefore, it's the greatest divisor of A and B. Make sense?
Yeah.
So first off, let's show that D divides A. Assume by way of contradiction that D doesn't divide A. Okay? That means I can write A equals some amount of D's plus R, where R isn't 0. When I do D divided by A, or A divided by D, I'm going to get a non-zero remainder. If it was a 0 remainder, then D would divide A. So when we write it this way, this R isn't 0. The remainder is not 0 when you take the division of those two. Good? So, in other words, we get R is in between 0 and D. So here's the crux of this line. Our remainder is between 0 and D. Now, since we know that D is equal to AX plus BY, because D is inside this set, so there's 2 X's and Y's such that D equals AX plus BY, right? Then I'm taking this line, what does R equal? R equals A minus QD. And now I'm going to use this information to make a substitution for D.
Okay.
Okay? So R is equal to A minus QD, that's what we're getting from right here. And then we're going to substitute in with that D with this substitution. So R equals A minus QD, substitute in for D. R equals A minus QD. And then I'm just going to get all my A's together and all my B's together.
All right.
oops, I want this to be b and negative y. You get with the algebra going from here to here?
You're basically distributing the cube and then factoring out A and B, right?
Here, I forgot to get my cube over here. Right? Negative cube. Is that right?
Should
A is 1 times A, negative QAX, negative QAX, and then we're going to have negative QBY, negative QBY.
So what's the 1 minus QS? Why is there 1?
1A, A times 1 gives us back A. A times negative QX gives us negative QAX. Good? See all the terms? Okay, so notice R is equal to A times some integer plus B times some integer. Right?
Yeah.
So R is in here. It's A times some integer plus B times some integer. We know that R is greater than 0. And we know that R can be written as some integer times A plus some integer times B. So if it's greater than 0, and it can be written as some integer times A plus some integer times B, it's in D. And the last thing we know about R is R is less than little d. So we have R is in big D and R is less than little d. Impossible. This is the least element of big D. Good?
And that proves that D divides
D
A.
has to divide A. And you can do the exact same thing to say that D has to divide B.
How does that prove that D divides A?
Right here?
Yeah.
Assume by way of contradiction that D doesn't divide A. That leads to an impossibility.
Oh.
Therefore, D does divide A.
Okay.
Proof by contradiction.
Right.
And then we can do the same thing to prove that D divides B. Nothing weird there, right?
Mm-hmm.
And so now we've proven up to here that D divides A and D divides B. Now we need to prove that.
Would that also imply that D divides X and Y?
No.
Why?
It would imply that D divides this term and this term. But it doesn't mean it divides X and Y just because it divides A and B.
Okay.
Good? Okay. So now the last part that we need to do is we need to show that if there is some other common divisor of them, E, so if E is a common divisor of A and B, so if E divides A and E divides B, then E is less than or equal to D. And if we can show that, then we've shown that D is the greatest common divisor of them. Make sense?
Yep.
So, suppose B divides A and E divides B. Then E divides AX plus BY. E divides AX plus BY. Which they're jumping to E divides D. Which gives us that E is less than or equal to D. Because D is positive. Yeah, let's make sense of this because we've already proved this, it references a previous exercise that we did in class.
Yeah, it's the trend,
So let's think for a second. We know that E divides this. So we know that D divides A and D divides B. So let's write through some scratch work real quick. We know that E divides D times some number and whatever, plus D times some number N, whatever.
what? Why?
I know that D divides A, so D times something equals A. That's something times X, I'm calling M.
Oh, okay.
I'm just thinking, I mean,
All right.
maybe put like a big X here and a big Y here, some different numbers that are still just numbers.
Right.
So if E divides
Then you can factor out the D.
that, yeah, that implies E divides D times X plus Y.
So E divides D.
So E divides D. There we go. So that wasn't too hard to
Yeah.
finish putting together. So E divides D, because D times something gives you, well, I guess you could still work with this one, but you see how you do it, right? E times something equals D times something, therefore D equals E times something, therefore E divides D. And since D is a positive number, E has to be less than or equal to D.
Right.
You can't get a positive divisor bigger than the number. It can only be as big.
By definition, right? Is it by definition or is it something else?
Well,
No, it's easy to imply, right?
it's an easy leap for our brains to make.
We need to state that out in the group?
Well, in order for A to divide B, what does that mean? That means A times some integer is equal to B. And if I know that this is positive, this can't be negative. If A is positive and B is positive, this can't be negative. The smallest thing I can put there is 1. Anything bigger I put there is going to make it bigger.
Right.
Okay, so E is less than or equal to D. Therefore, that puts it all together, 8. Therefore, D is equal to the GCD of A and B, which is what we were trying to show. So now the next part is going to be, okay, so I know that when I make this as small as possible, its sum, when I make this a small positive integer as possible, I know sum gives me the greatest common divisor, but how the heck do I find that x and that y? And it turns out we can use Euclid to find that x and that y. So, let's see it in action. What's the numbers that they want to use? We illustrate this method by finding x and y such that 431x plus 29y. So we're looking for x and y such that 439x plus 21y is equal to 1, which is the GCD of 439 and 21. So chances are, on your test, I'm not actually going to have you find the greatest common divisor of two numbers. I'm going to have you do something like this. Find x and y that satisfy this equation, and finding the GCD is part of it. Using Euclid is part of it. So I'm going to show you how to do this using Euclid's algorithm, and we call this extended Euclid, and you'll see why we call it extended Euclid here in a second. So you do Euclid's algorithm exactly the way you expect to do it. So we start out with 439 is equal to how many 21s do we need to get 439? 20? Did I do that right?
Maybe 21. No?
20 21s, and that's going to be plus 19. Did I do that right?
Yeah.
20 21s plus 19. So that was the first step of Euclid's. Now remember, we don't use 1 into parentheses. It was 21 was what we were dividing by. This was our quotient. So now we got 21 is equal to 119 plus 2. And we get 19 is equal to 9 2's plus 1. And then we get 2 is equal to 2 1's plus 0, and we're done. Whatever our last b was when we got 0 is our common divisor. So 1 is our GCD, right? And typically when I do it, I stop right here. This is far enough. Once you get down to what you know is your GCD, you can stop. And now we're going to reverse steps going back up. We're going to solve this for the remainder. Let me make sure I don't do this wrong.
Reverse steps going back.
Yeah, you'll see what I mean in a second, but make sure I didn't make a mistake here. Because those numbers should be there, those numbers should be there, and then we have that number. Okay, so rewriting this equation in terms of what its remainder equals, in terms of its remainder. So I'm doing its remainder equals what? 1 equals what? Solve for, put 1 on its own side of the equation, in other words. Put the remainder on its own side. So you're going to say r equals a minus qb, in other words. So 1 is equal to, and this is going to be kind of verbose, 119 minus 9 2's. You see what I did there? Just getting 1 on its own side of the equation. Okay? So I'm keeping 1, I basically moved these over here, and I'm being very explicit about what my coefficient of that 19
So you're
is.
trying to find when those numbers are A and B?
I'm trying to find x and y such that when you plug in that x and y, you get 1 out of this. I'm trying to find x and y to satisfy this equation.
Right.
That's what I'm trying to get. So, for each of these equations, you're going to write it in terms of its remainder. 2 is equal to 121 minus 119.
So why are we writing out the factors?
Why?
Why are we doing 121 rather than just 21? Or 9 and 2 rather than just 18?
Oh, because we're going to be doing substitutions here. So you'll see it when it all comes together. So first, go down until you get the GCD. Second, write each line in terms of its remainder. This one is 19 is equal to 1,439 minus 20 21s. Good?
Yes.
Okay. Now, we're going to take this bottom equation, 1 is equal to 1, and then we're going to substitute the 19 and the 2 from whatever numbers are here should also be up here. So we're going to substitute 19 using this equation, and substitute for 2 using this equation. So substitute these numbers not in parentheses, in terms of these numbers. Ultimately, what am I trying to do? I'm trying to rewrite 1 in terms of 439 and 21. When I rewrite 1 in terms of 439 and 21, whatever those numbers are, x and y, are going to be my x and y that satisfy this equation. So let's just keep going. So now, instead of 19 here, I'm going to do this substitution. 439 minus 20 21s. You with me? That's 19. I'm substituting it for 19. So we're rewriting this equation. 1 is equal to 19 minus 9 2's. Here's my equation for 2. I'm substituting the ones not in parentheses.
Okay, sorry, why are we doing this?
I'm trying to get 1 equals something times 439 plus something times 21. I'm looking for the x and y that make this equation equal to 1.
Factor out the 439 and 21, like by grouping, or?
Yeah, you know what? Let's not do this all in one go. Maybe this is, there's a more methodical way to do this. Take the smaller of these two numbers and substitute it. Let's do that. So this is 1 is equal to 119 minus 9, and substitute for 2. What's 2 equal to? It's equal to 121 minus 119. With me? Now, combine all your 19s and 21s together. How many 19s do I have? I have a 119 plus 9 19s.
Minus 19s?
Minus 9
plus.
minus 1.
Okay.
So 1 plus 9 is 10. So I have 10 19s. And how many 21s do I have? I have negative 9 21s.
Right.
Good? And that's still what 1 equals. So now instead of having 1 written in terms of 19 and 2, I have 1 written in terms of 19 and 21. Take the smaller of these two numbers and substitute. What's smaller, 19 or 21? 19. So we're going to do this substitution for 19. So 1 is equal to 10 19s. 439. Plus negative 9 21s. With me? I just substituted in the 19 using that exact equation.
Okay.
Okay? Now, combine like terms. Collect all your 439s and collect all your 21s. How many 439s do I have?
10.
And how many 21s do I have?
Negative 209.
Negative 209. So, 1 is equal to 10 times 439 plus 209 times 21. In other words, negative 209. In other words, x equal to 10 and y equal to negative 209 are the two integers that satisfy this equation. So when I give you this equation, I say solve for x and y that satisfy this equation.
That's interesting.
Here's a solution. X equal to 10, y equal to negative 209.
You've never done. It's interesting that you can solve an equation like with two variables and not have to.
Well, notice there's infinite solutions to this.
Yeah.
We just found a solution.
Can we do that again?
Yeah.
Yes, we can. Do you want to do it with these numbers or do you want to use different numbers? Okay, let's do different numbers. Let's go get those numbers that we used before. That way we have a guarantee that we don't make a mistake. You know what I mean?
Which
Sure.
ones?
From earlier when we were just doing Euclid. So 221, 689 and 234. So I want you to find me numbers, x and y. Just cancel that. Find x and y such that x times 689 plus y times 234 equals 13. 13 happens to be the GCD of those two. I just already knew that. That's why I went back to this problem. So I'm telling you, find x and y that satisfy this equation. Okay?
Right.
My question, because there's infinitely many solutions, what are the requirements that we're looking for on x and y?
So far, we haven't limited it. We'll talk about how to find all the solutions, but we're going to start with a solution. So we're going to do more with this.
Why is the solution that we choose relevant? Why is it important?
How do you find a solution? Once you find a solution, it's really easy to find all the solutions. I shouldn't say really easy, it's easier to find all solutions when you find a solution. So,
are we only looking for integer solutions?
yeah, we're only talking about integer solutions.
Okay. Okay, that makes more sense.
Okay, so we only want integer solutions. We're only allowing you to pick integers for x and y. You need to find x and y such that this is equal to 13. Good?
Okay.
Okay, so that's our problem. Now let's do it. The way you do this is you start with euclids, finding the GCD just like you're used to. So I have 689 is equal to how many 234s? 2. 234, right? Mm-hmm. Plus, and then what was it?
221, I think.
221.
Right?
Yeah.
34, that gives us 68 plus 21 is 89, and then the hundreds come out. Okay, that's right. So, and now that you've seen extended Euclids, I'm also going to do at the same time rewrite this in terms of its remainder. That 221 is equal to 689 minus, or plus, we'll do the negatives like this. Negative 2, 234.
What?
I'm rewriting this same line
Why is it
in
negative?
terms of its remainder. I'm moving this to the other side. So instead of a 2, now it's a negative 2. I'm moving this factor on the other side of the equation.
Why don't you just say minus positive 2?
You could,
It's easier. It makes more sense. Just do that.
okay, you'll see where this comes back at you. But sure, if that helps you think about it, that's fine. There's nothing wrong with that. Okay, continue. So now we have 234 is equal to 221 plus, what is that? 13?
Mm-hmm.
So I'll rewrite this in terms of its remainder. 13 is equal to 234 minus 221. Okay? Now this is our GCD. Right? So we're done with Euclids. So now I'm trying to find numbers x and y that make this equal to 13. So I know that 13 is equal to 234 plus negative 221, right?
Mm-hmm. Oh, okay.
Right here.
Yeah. All right.
Right, yeah.
Pick the smaller of these two numbers and substitute in.
Why do we pick the smaller of the two and substitute?
Because we're guaranteed to have written the smaller of the two in terms of bigger numbers. Notice 234 is already one of the numbers that we want. This 221 isn't one of these numbers. So I need to write 221 in terms of these numbers. So 221 is equal to 1 of this number minus 2 of this number. So I'm going to substitute in for 221. That's all I'm going to do here. So 13 is equal to 234 plus negative 1. 221 is 689 minus, I'm going to do plus now, negative 2 234s. Good? I just substituted in for 221. Collect like terms.
This is weird.
It is weird. Collect all my terms, all my 234s and all my 689s. How many 234s do I have? I have 1 here, and I have 2 here. So I have 3 234s. 1 234, and
Yeah.
negative 2 times negative
Right.
1 is 3 234s.
Yeah.
So I have 3 234s. And how many 689s do I have?
Negative.
Only negative 1 of them. So 3 and negative 1 are the numbers that you plug in for x and y to make this equal 13. Right?
So the more lines you have, the more
Substitutions you have to do.
you have to do.
You have to keep substituting all the way until your top one, because your top one is going to be in terms of the numbers that are over here.
Right, okay.
Good? So that's what we call extended Euclids. Okay, I think they have one more here that takes a few more steps. So let's do one more that will make us do more substitutions. So the numbers that they have are 431 and 29. So 431, and we already know that the GCD of those two numbers is 1, is what they're giving us. Yeah? Understand what we're doing? No? No point in doing it?
What?
Is there any point in me doing it? Or do you guys like to go? Do it?
Yes.
Okay, let's do it. So I'm trying to find the x and the y that make this equation equal to 1. I'm going to start by finding the GCD. I know that the GCD between 431 and 29 is going to be 1, but let's start doing Euclids. So Euclids, we say 431 is equal to how many 29s are we going to get? 7.
Wait.
More than 7. Question is, will we get a full 16 or will it be 15? I'm guessing it's going to be 15, but I'm not positive. Yeah. 15 29s. And what is 15 times 29? $435? Oh, crap. It's going to be 14. $435, well, probably faster than just do that now. So 4 times 9 is 36, 8 plus 3 is 11, 0, 9, 2, 6, 0, 406. So 406, and we need to get to 31, that's going to be 25. Now rewrite this in terms of its remainder. 25 is equal to 431 plus negative 14 29s. Good? Nothing more on the first line? Continuing with the next line. So 29 is equal to 125 plus 4. Right? Write this in terms of its remainder, we get. Maybe we should have you guys do this.
Probably good again.
Yeah, let's have you guys do this. So let me erase this. You guys do it. And then once you've gone through it, then I'll go through it and you can compare with what you did. So pull out the paper and a pencil and see if you guys know how to do this. Because this is going to be on the test. 100% no question about it. So pull out paper and pencil, let's see if you can do it. And then I'll do it on the board, and let's see if you get it.
My question is, what distinguishes your x and y that we're finding from all the other pairs? What's special about it?
We just now have a way to guarantee us to get us one.
So if we counted different ways, it wouldn't matter.
Sure.
I'm just trying to see if x and y have any peculiarity, or if it's just because this is the way we know how to find them.
X and Y have any... Maybe there is only one solution, come to think of it. No, there's got to be. I'd have to think about it more. But it's a way to guarantee us at least one solution. Geez, are we only going to get through one section?
We have another two sections. Isn't this the second section?
No.
Not the second section. Wow. Dang.
Well, that's okay. Modular arithmetic.
So you start out by saying 431 is equal to...
Here, find the GCD of 431 and 29.
I just totally spaced. That was weird.
Do you know where to start?
Okay, what are you asking us to do? Sorry.
Find x and y that satisfy this equation.
So we start out by saying
Just do it in your head.
431 is equal to a certain number of units.
Yeah. Plus some remainder.
Plus
You're
R.
writing 431 is equal to QB plus R,
Yeah.
where B is 29.
Didn't we just do this?
I did most of it, then I stopped, erased.
Yeah.
And said it'd be better if you guys did it and then watch me do it. Because I think you're going to get stuck on some part of the process when you go through it. And I think you getting stuck in and me doing it will help you get past that first leap.
That doesn't make sense at all.
So then you have 1 equals something. And it's not necessarily 430 in terms of 431.29.
Right.
But it's in terms of numbers that you know how to substitute back in.
And then the smaller of the two you.
Substitute in the smaller of the two. Then collect like terms. Then substitute in the smaller of the two. Then collect like terms. Keep doing that until you can't do it anymore. And you're going to be left with some number of 431s and some number of 29s is equal to 1.
Okay.
Maybe I'll just start writing it up as you guys are doing it. So we don't have to spend too much time watching you do it. We already know how to do it.
So, in our examples, we went out and did it kind of one at a time where we took several steps to do each of the smallest numbers. Can you kind of just combine them into one equation and do it all at once?
You're still going to have to do, it only saves you one substitution in the long run.
Okay.
And it'll probably end up confusing you because you'll be substituting for the same number multiple times. So I substitute one at a time. go through it then and see where you made a mistake. So starting with euclids, you got 431 equals 14 times 29 plus 25.
Right.
Rewriting the remainder, you get 25 equals 431 plus negative 14 29s. Okay, next line of euclids, we now get 29 equals 125 plus 4. Solving for the remainder, 4 equals 29 plus negative 125s. Okay, and then you get 25 as 6 24s plus 1. Or 1 is equal to 25 plus negative 6 4s. And then obviously, this is 1 equals something. So we know that, okay, here's our GCD. Right? It's the number that was right here.
Right.
And then from this is the one that we're going to start substituting into.
Right.
So rewrite that down here. 1 equals 25 plus negative 6 4s. What's smaller, 25 or 4? 4 is smaller, so that's what we're going to substitute in for.
Right.
And we're going to use that substitution. So we have 1 equals 25 plus negative 6. 4 is doing our substitution. We have that. When you multiply terms, you end up with 7 25s and negative 6 29s.
Yep.
Okay. Now we're going to substitute in for 25 using the top line. So you have 7 25s plus negative 6 29s. When it's all said and done, you should have 7 431s and negative 104 29s.
So I got 106. I probably just did my math wrong.
106.
There you go.
Yeah, 7 times the 4 is going to be 28.
I for some reason. Yeah, no, I didn't know. In my opposite side of arithmetic, I just messed up a little bit.
Okay. And then when you plug in those numbers, it comes out. So it is 7 and negative 104.
Yep.
Okay, so that's the type of problem that's going to be on the test. Good? Okay. Quick definition, not going to bother writing this out explicitly, but we say that two numbers are relatively prime if their greatest common divisor is 1.
Okay.
So think of an example real quick. 9 and 8 are relatively prime.
Okay.
Make sense? Even though 9's not prime, 3 goes into it. 8's not prime, 2 goes into it.
Is there a notation for it? Or do you just say they're relatively prime?
They're relatively prime. That's all we say. There's no notation for it. Here's another way to say it. Two numbers are relatively prime if and only if their only common divisors are 1 and negative 1. Same thing as their greatest common divisor is 1. So all prime numbers are relatively prime to any number, but two numbers that aren't prime can still be relatively prime to each other, like 8 and 9. Okay?
Okay.
Two numbers, A and B, are relatively prime if and only if you can write AX plus BY equal to 1. So I know that these two numbers are relatively prime because I can find two integers x and y that makes this equal to 1. Right?
Also, that's a really good way to test if they're relatively prime. Two random numbers, you can test the relatively prime by trying to do this.
Well, you don't need to do this part of it. You just need to take the GCD of the two of them, and if it comes out 1. But if you know that two numbers are relatively prime, 431 and 29, if I know that those two numbers are relatively prime, then I know that there has to be an x and y that makes this equation true.
Okay.
There's an equation x and y that makes this equation true if and only if the two numbers are relatively prime.
We're not going to prove that.
You can look at the proof for it. It's really simple because it comes from the fact that we already know that the smallest this can be, the smallest positive number that you can get of this form is the GCD. If it comes out to 1 and 1's GCD, then the two numbers are relatively prime. Right? It almost immediately follows from what we've already proven. It's corollary, so I don't think that there's anything to it. Same with proposition 36.10. It's already one that we talked about in doing that.
What's the difference between a theorem and proposition?
There isn't.
So why do we use different names?
So the author Well, how can... I'm sure that he explains his verbiage for why he uses one over the other. But, so, proposition and theorem, I'm not sure how to give you good intuition for what the difference is between those two is typically going to be, except for that a theorem's probably going to have a lot more continued use versus proposition.
Okay.
For how this author's using it, I mean, in general, a proposition hasn't been proven yet. It's a theorem once it's been proven. But the three words that you typically have for a theorem are a corollary, a lemma, and a theorem. They're all the same thing.
What are, I noticed that the authors used lemmas before.
Typically, you use the word lemma when you're just proving it to help you do your main proof. So typically, lemmas help you with your main proof, your theorem. And then corollaries are really small proofs that immediately follow from your theorem. So most authors use that convention for lemma, corollary, and theorem. I'm not sure how to draw a fine line between how he's using proposition and theorem. But anyways, let's try and give you some quick intuition for modular arithmetic before we leave. So that was all the GCD stuff. Next we're moving to something that's a bit different, called modular arithmetic. And this is going to be kind of like calculating this. You're going to be calculating a lot of mods for modular arithmetic. So we start out with defining a system of numbers that aren't all the integers. So when I do a notation, I do z with a subscript here, n. This is shorthand for the set 0, 1, 2, 3, up to n minus 1. There's n elements in it. 0 through n minus 1.
What about the negative numbers?
Nope. Starting from 0 going.
So why did we use z instead of n?
Just convention.
Okay.
And then, so if I do z of 10, for example, then that is 0, 1, 2, 3, 4, 9's the last thing in there. Okay? That's what we mean by a z sub something. Okay? Now what we're going to be doing is I'm going to give you some set of numbers like this, and you're going to be and we're going to define what it means to add numbers together in that system, what it means to subtract numbers from each other in that system, what it means to multiply numbers in that system, and then most importantly, what it means to divide numbers in that system. So let's start with adding numbers in that system. What is 3 plus 4 in that system? 7, right? Nice and easy. That wasn't hard. But what is 7 plus 4 in that system?
I guess you could call it like 9 mod 2 or something.
Kind of broken, right?
Yeah.
So first off, when we're adding in these systems, we're not doing regular adding like we're used to. So we do a circle around the operation that we're doing for modular addition. And the definition of this, 7 plus 4 in this system, Z10, assume we're talking about Z10, not this. It's always in the context of some set. It is 7 plus 4 mod 10. That's our definition for it. So when I have A modular arithmetic plus B in any set Zn, that's equal to A plus B mod n. So in this case, 7 plus 4 is equal to 1. Good?
Kind of just starts.
It's cycling. It's circling around. That's exactly what it's doing. Right? What's 9 plus 9? 8. There you go. What's 7 plus 8?
5.
5. There you go. What's 3 plus 3 plus 3 plus 3? 2. Wonderful.
Okay, wait, what?
You good with this?
Sure.
Sure?
Yeah.
this system, what does it mean to add?
It's kind of just like addition within just a section of integers.
Right.
In a set.
So when we say A modular addition B, that's equal to A plus B mod the Z that we're in. If we're in Z10, we're modding by 10. So 7 plus 4 using the modular arithmetic addition is just 7 plus 4 like you're used to, 11. Now modded by 10 is 1. You good? Notice these are the only numbers in our system. When we're talking about Z10, all we have are the numbers 0 through 9. It doesn't make sense to say what's 18 plus. No, 18 is not a number. Good? Yeah, it's like when you're dealing with the real numbers, and I say, what's the square root of negative 3 minus 7? Well, not a real number. Same kind of thing. Okay. So that's how we define addition. Subtraction, very similar thing. A minus B in the system. We're still going to do the A minus B like we're used to, and then mod it by n. Now, modding by n, modding negative numbers by n, remember, doesn't always work the way you think it works. So, for example, what's negative 7 mod 10?
2 plus 4.
No.
No, it's 4.
Negative
No.
7 on 10.
Yeah.
It would be negative 2 plus 4.
No. What are you guys into? What's part? So, we're taking negative 7 and we're dividing by 10, right? So A is negative 7 is equal to some number of 10s plus our remainder. Our remainder has to be positive. So this is negative 1 plus 3.
Oh.
Oh.
Good?
Yeah.
Okay.
Okay.
So what's negative 5 mod 10?
Would be
Negative 2.
No.
No. Negative
can't be
1 plus
negative.
5. Wait, what?
No.
Negative 5 mod 10. Negative 5 is equal to
Negative 2. No. Is equal
1.
1.
negative 1. 5! It's equal to 5!
That's what I said.
You did?
I said negative 1 and 5.
Oh.
And then you got me tripping.
For some reason, it's just gone out of my head. But
Alright, what's negative 3 mod 10?
Negative 1 or 7.
It's 7. It's not negative 1 7. The mod is just 7.
Right.
Right?
The divide is, how do you say that?
The div. The div is negative 1. The mod is 7. Right? Okay. What's negative 8 mod 13? 5. Good job. If it's too hard for you to do this math in your head, just keep adding multiples of what you're modding by until you get a positive number. Right? So if I'm looking for negative 7 mod 10, negative 7 is too hard, add 10 to it, and you didn't change it. Do you understand why adding 10 to it wouldn't change it?
Because then your remainder doesn't change.
Your remainder doesn't change. You added your remainder of 0. Adding 10 is adding your remainder of 0. You're not changing your remainder by adding multiples of 10 when you're modding by 10.
Right.
If you're modding by 13, adding 13 isn't changing it.
So your example was negative 5.
I don't know what I said. I think I said negative 8 mod 13.
Okay.
So then
It's
add
5.
13 to negative 8.
Yeah.
That's weird.
Okay. Yeah.
Okay? That's the kind of thinking that's going to help you when you start doing the difference. So now we're in this mod system. If I say what's 5 minus 8 mod 10, what is it?
5 minus 8 mod 10.
Uh-huh.
That's negative 3 mod 10, which is
7.
7.
Huh.
So, I can't remember what I said.
But
I said 5 minus 8 is 7. 5, modular arithmetic.
That's so weird.
5 minus 8 is 7.
Is there a way to say that?
Yeah, he gives the exact verbiage in the book. I don't know where I left mine. Okay. Okay? Works the same way with multiplication, the way you expect. The only weird one is division.
Why are we learning a whole new word?
Huh?
This is so weird.
Basically, what's the point of this?
Well, what's the point about the integers?
Seems a little more useful.
Yeah, why do whatever, I don't care.
In reality, dealing with these types of operations on simpler sets, because I mean this is a much simpler set than the integers,
Oh yeah.
helps you come up with generalizations that apply on other sets. But modular arithmetic, I mean this is, well, where is it useful? When you think about clocks, you're doing modular arithmetic all the time. It's 1 o'clock now, what time will it be in 24 hours? 1 o'clock.
Yeah.
Whoa, what?
So with the clock, if you think about in terms of army time, you're doing mod 24. There's one example of using modular arithmetic in everyday life.
Alright.
If you do it in army time, if you do it just by where it's pointing on the clock, it's mod 12.
Alright.
Right? Except for you're not using 0 through 11, you're using 1 through 12.
I see.
So, be well, it wouldn't be my anything because there's no 0.
Right. So if it's 5 in the morning and you go back 8 hours, what time is it?
It's 9.
3.
Well, do it in terms of army time.
No, I don't know.
Oh, you can do it in terms of that. I can't remember what I said now. I said 5 minus 8. If you think about it in terms of 12, then what's it going to be on?
On the 9.
The 9, because he's adding 12, right?
Oh yeah.
So, same thing.
Can I take a break?
Well, we can just call it good. So there's your introduction to
What?
class is basically done, so we'll just call it good there.
Wait, what time is it? I can't
Look at
recall.
You can't, it's almost 4.
I'm just kidding, I can't. Okay, I'll be right back.
So there's your intro to,
That's all that section is.
well, multiplication works the exact same way that you would think it does. It's when you get to divide that it's a little bit harder to do.
So
The same reason that dividing in the integers is a little bit harder to do. Right?
Not that much harder.
It's easy to multiply integers together.
Yeah.
But when I say, what's 127 divided by 13?
You have to write it down.
Then you're going to end up with some quotient and some remainder.
Yeah.
And so we're going to run into weird problems when we start trying to define division over here. And we're going to come into the concept that we call the multiplicative reciprocal.
And are we going to talk about that today?
No. We'll leave it there. I just wanted to introduce you to the basic arithmetic so
Is
that
it in this section at all?